Okay, please turn to page 396 in study book and practice exercise 8.11. And for this case, guys, you are required to find the self-inductance of the coaxial cable, which has the inner radius of A for the first wire, for first inner conductor, and then it has the radius of B for the outer conductor. And then, guys, the region between the inner and outer conductor is filled or made by the non-homogeneous material, which having this permeability of 2 mu naught over 1 plus r, right? So if you can see from this question, guys, so this from this mu, it has a variable of r. It means that it is a non-homogeneous case. So we just proceed as usual to find the inductance. Alright, so since we have covered two different structure of wire before, a single and two wires parallel, so now we have already the idea on how to find the inductance or self-inductance due to the single wire. So now this structure, guys, is composed from the single wire inside the coaxial cable, and also it has the outer conductor. So we can simply reuse, right, that solutions that we have derived together last time. So from this diagram, we know that the L net actually is composed of the L internal plus L external, and we have derived already this L internal that due to this single wire, which the expressions can be expressed here. The L internal is equal to the mu L over 8 pi Henry. Okay, guys, so that's the L internal expressions due to the wire inside this coaxial cable. So now our task to find the L external or the external inductance outside here, right? So now again we have assumed that this is a very long coaxial cable, whereby the L actually is much larger than the radius here. So we can simply apply the Ampere's circuital law to find the H field that actually exists outside the wire or outside the internal wire, which is in this region, because now this is our regions of interest. So again, applying the ACL, close integral H dot dl is equal to the I enclosed, right? So now again we have the H is equal to the I 2 pi r part phi directions. So guys, let's assume that within this conductor, it has the current of I flowing in positive directions of Z, and assuming that the outer conductor here flowing the return current, which is in negative Z directions. Okay, so they have same magnitude of current but in different directions. So now since we are choosing this is our region of interest, so that's our point of interest, so you can simply draw our Amperian loop, right, that pass through the point and must be closed. So this is our radius of Amperian loop, R. So that's why from this expression to find the I enclosed within this loop, so only appear the positive I current, so just put here positive I. So that is going to be our H expressions or the H field that actually exists within this region of interest. Okay, guys, so again, applying the same formula that we used last time to find the inductance, we have to use the magnetic energy equations. So the first step now, finding the magnetic energy expressions. The magnetic energy can be obtained using these expressions: half mu the H squared dV. So guys, now let's put the value here. Now the mu, guys, here is no longer mu, but now we have the non-homogeneous expression, so just replace this mu equal to this mu. So now we have here 2 mu naught 1 plus r for the mu here, and then the h squared actually come from this one, so that is going to be our h magnitude. Right, so now we have I squared and 4 pi squared r squared, right, because we square of this h magnitude. And now replace the dv, which are dr dv dz. Okay guys, and then let's simplify. So we have here 2 down here with 2 up there, and then we have here r up here with r1 down here, so left 1. So take out the constant outside out of the integral parts. Now we have here mu I squared, right, so over 4 pi squared, and then now we have 1 over r, 1 plus r dr dv dz. Okay guys, so this r come from here, and then this 1 plus r come from here, so just multiply them. Okay, so now let's set the limit. So again, the z along the line becomes 0 to L, our assumption, so the phi 0 to 2 pi for the complete set circular cross sections. And then the r here guys, actually we only concern or between A until B, right, because that's going to be our region of interest. So by right here should be A to B. Okay, so if you solve this part, you have 2 pi L, so let's put here mu naught I squared 4 pi squared. Now we have 2 pi L come from these two integration paths, and then now we have to simplify this form of integrations. Now we have, you can simply change to 1 over r minus 1 plus r, right, again from A to B. Okay guys, so that's the conversion from this form into this form. So now you can simply solve easily using related transformations of integrations. So now we're gonna have here, so let's simplify this part. Now we have here pi down here, 2 up there, and 2 left down. So now let's proceed. We have here mu naught I squared L over 2 pi. Then guys, now I'm gonna have here 1 ln B over A plus ln 1 plus B over ln plus 1 plus A. Okay guys, so that's the result of this integration, whereby we can have ln term and then limit B over A, then here 1 plus B up over 1 plus A down. Okay guys, so that's the magnetic energy expression for these coaxial cables, for sure in joule. So now we are going to use these expressions to find the inductance value. So the L can be obtained using these expressions: 2 magnetic energy over I squared. So just 2 over I squared, and then put all the value, the expression mu naught I squared over L over 2 pi. Now I'm gonna have here ln B over A minus ln 1 plus B over 1 plus A. Okay, yes, so let's simplify. I down squared down there, I squared up there, the 2 up there, 2 down there, so left only pi. So the L external of this coaxial cable is going to be this mu naught L over pi. Now we have here B over A minus ln 1 plus B over 1 plus A. Okay guys, so let's add up with the previous L internal that we have derived previously during last lecture. So now to find the L net or L total, just add up between L internal plus with the L external. So let's combine them and factorize. Now let me factorize. Now we're gonna have here, we'll just combine them. So here is mu L 8 pi plus mu naught L pi, now ln B over A minus ln 1 plus B over 1 plus A Henry. Okay guys, so this is the final expressions of the total inductance that due to the coaxial cable. So I hope you can try yourself and make sure you're gonna have the same result as mine. So let me know if you have any questions. We will try to help you. So okay, thank you guys, all the best and take care.